So that's the agenda, and we should get through most of it. But as I say, we may not get through that business case at the end. So here's the example I want to take you through. It's an issue concerning minor sexual offences on the tube and on the buses. It's not a minor offence if you're on the receiving end, of course. And it's the kind of thing that is very pernicious and annoying. But yet, if it's that, or do you try and spend your time dealing with people trying to kill themselves, it tends to be a bit of a kind of poor relation. Same with pickpocketing and other kinds of minor offences on the tube. The British Transport Police take it very seriously, and they really wanted to transform the way in which the offences are perceived. Now, some of you may be old enough to remember when it was quite common for people to be drinking on the tube and on the buses. There were cans of beer around and that kind of thing, and that's almost unknown now. That almost doesn't happen, right? So effectively what they're trying to do is achieve the same kind of transformation in regards to these and other minor offences. So the London transport system becomes as basically friendly and safe as it can possibly be. The problem is that very few offences are reported. It's estimated that, and we don't know for sure, but it's estimated that less than 10%, perhaps as few as 5% of offences get reported at all to the police. And of course, the police say, well, if we don't hear about them, we can't do anything about them. And over the last 3 years, they pursued a project on this, an initiative called Project Guardian, designed to really tackle this. And key to this was a campaign to get the offences reported. So you may have seen headlines in the newspaper about, offences on the tube have gone up. No, they haven't. Reported offences on the tube have gone up. Right? Not the same thing. Not the same thing. The police wanted this number to go up, right? Because that means that they can be actually doing something about it. We don't know exactly, but maybe the typical offender commits something like 10 offences per quarter, maybe 5. But because it's such a kind of hidden offence, no one really knows what's going on. A lot of this data is estimated. So the strategy that BTP, the British Transport Police, followed was that the 3 planks of this was to raise public confidence that the offences are taken seriously. Secondly, to put victims at the centre of the process. So when people complain, you really take them seriously. You really show that you're trying to do something about it. And there's a real skill involved for police officers to detect all kinds of minor offences, including pickpocketing and so on. And amongst the more experienced officers, there are some very, very clever people who know what kind of slightly odd patterns of behaviour to watch for and say, oh that guy, you watch, he's going to pick someone's pocket in the next 2 minutes. It's a real kind of tricky skill that they have. So they wanted to build up that skill. Apart from these numbers, pretty much, we don't know much of this. We know about our own activities, like we know how many officers we've got. We know how many of those officers we deploy to certain places. So there are certain hotspots on the transport network where these offences are quite common, and there are hotspots in terms of time of year as well. More common in the summer, less common in the winter. We know about that, but what we don't know is the actual offences. We don't know very much about where they're committed, because if they aren't reported, we don't really know either. So what I'd like to invite you to do is help me actually make a start on this model, if you'd like to do that. Okay, get your laptops out then, with your friend. If you're not sitting with a friend, make a friend now, right? One between 2 is perfect. And go to sdl.re/blank. This is a system dynamics modeling tool. And when we build system dynamics models, the first thing we do is figure out what time scale it's going to run over. We're going to run this over, go to 24. We're going to do this in quarters. And we've got 3 years back, 3 years forward, so that's 12 quarters back and 12 quarters forward. And I think I just told you that the number of offences reported has risen from about 150 per quarter to about 300. Okay? So just click on that thing called a variable there, and give it a name, reported offences. Okay. And you'll see it's got a nice little chart there. If you set the maximum on that chart to 500, and then just drag your mouse pointer across the chart, rising to about 300, somewhere around time period 12. And we might, let me make the scale a little larger, maybe 800. And we'd quite like the number of reported offences to go up even higher and then actually come down, because we're going to actually stop the offences, right? So the reporting will rise because we're catching more of what's going on, and then we will have a sustained higher reporting rate, but the actual offences will be coming down. So the reported number will come down. That's what we would like to have happen, right? If you click on this little table tab on the right-hand side, you can see that what the simulation has done is it's actually put in, this is what we call our sketched time series. And what we do is we actually paste real data into that time series. And as I've done for the future periods, we actually sketch in what we want the future to be. And because the simulation doesn't know anything else, it said, well, my guess as to what the simulated number is it's the same as the sketch. You haven't told me anything else, so that's what it must be. Right? So we've got a variable called the actual offences. Always good to be clear what the units are. Oh, sorry. Yeah, hit the V key. It's complicated as that. Hit the V key, and you get a new variable. That's the actual offences. We don't know what that is, but what we do know, so hit V again, or actually if you hit Shift V, you can put in % of offences reported, and that will actually create the variable in one go. And I think I told you that this increase from about 5% to probably 10%. We might like it to go to 20%. So we'll set a scale for this variable. It goes up 20. And we think that number might have increased from 5 to about 10. So again, just drag your mouse across there, and we want that number to continue going up high. In fact, we'd like it to go up higher than that. We'd like it to go up to approaching 20%. We'd like 20% of people who are victims of this offence to go find a police officer and tell them, right? That's what it means. Now, if you click and hold in the little cloud there and just drag the arrow, it will join up to the thing you take it to. And the red arrow says, you've linked me up, but I don't know what to do with the relationship here. So I'm going to put in a guess as to what the actual offences have been. So click on the actual offences and put in a scale there of 10,000. And my best guess is that probably has done, I don't know. But I can check whether my guess is actually any good or not. And this is a matter of simple arithmetic. This is not exactly advanced maths. This is actual offences multiplied by %. And we can immediately see that I must have made some big mistake, because the red line and the blue line aren't even on the same order of magnitude. Oh, I wonder what the mistake was. It was because I forgot to divide by 100. Okay. So what this does, this method, and the same would be true of ABM and DES, they are to a degree self-validating. Mistakes can't persist, because if the result doesn't match what the real world is doing, then you must have made a mistake. This turns out to be very important, because in many situations we try to model. We've got bits of data. We've got a bit of data here, we've got a bit of data there, we've got a bit of data here, we've got a few missing things in between. Well, if you've got a theory about how all these things join up, And when you join them up and you make the maths work, and all the numbers and all the lines match, you can have quite some confidence that you're capturing what's really going on. As it happens, I'm doing a project with a guy on my distance learning course at the moment in the US, who is a deputy commissioner for a police district in the United States. And he has got, and you might imagine with what's been going on in the news in the United States recently, they've got a real issue about police legitimacy in the eyes of the public. So he's trying to do exactly this, which is piece together little bits of data. He knows about arrest rates, he knows how many people are in jail, he knows about complaints from the public. He's got all these little bits and pieces, and we're just trying to figure out how the whole system hangs together. It turns out that my guess on that sketch wasn't too bad, actually. I can perhaps improve it a little bit. Do I need it to be higher or lower? I need it to be a bit lower, don't I? You get the point, right? You're basically reassuring yourself that you're getting the thing right. And remember, all the time we're doing this, when we do this for real, the red line is real data. That's what we do. We put real data in the red line, and what we're trying to do is get the model to match the real data. So the next thing to appreciate about system dynamics is it captures this concept of stocks. Asset stock is a technical term, and in this case, the asset stock is criminals. And it's a bit more specific than that. This is criminals at large. The number of offences that are carried out is dependent on the number of people committing those offences, and we'll put another variable here called offences per person per quarter, and we thought that was something like 10. So we put that as a constant for the moment, and we can hide its little chart. We don't need it. And what we know is that this is arithmetic as well. No more advanced maths. This is actual offences is the number of criminals committing them multiplied by how often they do it. So if that number is 10 and that number is 4,000, there must be something like 400 of these people out there. So I'll put a scale on there of 500 because we're definitely going to get that number to come down. And what we'd like to have happen is we'd like that number, probably won't go down as sharply as that, but go down like this. Now, this thing called a stock has a particular characteristic. So just click that little button there, the two-headed button, and that forces the thing to use that sketch. So if my estimate here is right, then criminals at large multiplied by offences per person per quarter, it ought to match. It appears not to match, so maybe I got my estimate here a bit wrong. Maybe the number of criminals has gone up. Oh yeah, that's looking a bit closer. Of course, we don't. What we actually want is we want this number to come down rather more quickly. So we'd like it to. So the last little bit about the system dynamics method. Those are two of its tools: the regular variable and the stock. The thing about the stock is it can only be changed by something called a flow. Now, these asset stocks are things that exist at a point in time. So the classic examples are cash. So the cash in your bank account is an asset stock. The quantity in your bank account is the sum of every pound you ever paid in minus every pound you ever paid out, to the penny. There is no error term in that relationship, right? But assuming your bank hasn't made any mistakes. Right? Now, this is actually fundamentally important, because what happens in a lot of management is we try to explain things like this by statistical studies trying to treat this as the dependent variable and explain them in terms of independent variables such as the number of police on the beat or the state of the economy in the case of corporate results. The problem is, if you've got one of these things, between the independent variable and the dependent variable, regression methods cannot work. They just can't. Right? Because the value of that item, that stock, is precisely the sum of every individual who ever joined the stock minus every individual who ever left it. Now that means that the entire history of that stock is the only possible explanation for the outcome. So you cannot find a valid cross-sectional explanation for any performance outcome where accumulating stocks are involved. And this isn't an opinion, it's just an axiomatic feature of the way the world works. The amount of money in your bank account, it might be correlated with how many nights a week you go out, or how many kids you've got, or how many rich relatives you have. That might be a coincidental correlation, but it cannot be a causal explanation. The only causal explanation for the money in your bank account is all the money I ever paid in minus all the money I ever paid out. There is no other explanation for that. That is absolutely true, to the penny, with no error term. What that means is that we've got to explain this, which is new criminals per quarter. And that is a characteristic of these flow rates. They always have the units of the stock per time period. And we must have, I think we started this number at something like 300 over here. And it increased to 400. So maybe that number has been running at something like 10 per quarter. Now, if that number was running at about 10 per quarter, that is what would have happened to the stock. We started at 300 and something. We started at 330, 333. We added 10 per quarter. And if that's all that happened, that's what would happen to the accumulating stock. That's not what we want to have happen. We want a flow here of giving up per quarter. And with a bit, what we would like to have happen to that is we'd like that to kind of start increasing. So we can actually do that by having a formula in here, which is ramp, put in ramp 2, 13. That does it. Okay. What that says is that starting at time 13, I'm going to increasingly take people out of the stock of criminals every period. Appears not to have started early enough, and actually Project Guardian did manage to start things improving rather earlier than that. So now what we've got is we've got what looks like a valid explanation for the thing we're trying to explain. We just haven't quite matched the data correctly. Okay? So how long has that taken us? I think that's taken us about 15 minutes. That is the conversation I had with the guy in charge of this program. We didn't have workshops. We didn't go and ask lots of people their opinions. He knew those two numbers that we know. He estimated the other ones, and that's the model that we produced. That's why this process is easy. You get somewhere, you get impactful insights very fast. There are three possible reasons why this line followed that path. Reason number one is the flow rates of people taking up the crime. Reason number two is the flow rate of people ceasing to commit these crimes. And the third explanation is the change to their frequency. That's the only three possibilities for that change there. Revert to the presentation then, and just tell you a little bit more. So what is system dynamics for the system dynamics virgins in the audience? It's the use of quantified causal diagrams and simulation models to understand and manage issues that feature complex behavior arising from stock accumulation, which I've just shown you, and feedback. And I'll explain to you how feedback comes into this. The words here are quite important. There is a school of system dynamics which doesn't try to quantify these models. They do causal loop diagrams. They have significant successes in helping large groups of people to solve problems. But system dynamics itself actually goes on that extra stage, and it produces these causal explanations and simulation models that allow people to test policy. First of all, discover what's actually happening, and then test policy for changing what's happening in the way you'd like it to change. And these things happen everywhere. You name it, whatever field of human endeavour you want to talk about, you'll find it. And as I explained, spreadsheets and regression methods cannot solve these problems. It's not a question of, if you put enough monkeys on typewriters, you'll produce the works of Shakespeare. No, you won't. Right? You cannot solve these problems with spreadsheets and regression methods. It's extremely widely applied. I mean, you name a field and someone's done system dynamics of it. System dynamics is about improving performance over time. It's got no meaning for any problem that isn't about things changing over time. Right? If it's not changing over time, then it's not a system dynamics problem. But they've got these kind of characteristics. There is a history of things happening, and the situation might be getting better, it might be getting worse, but there is a history. And history matters for two reasons. Firstly, because of that accumulation thing, stuff that happened in the past is already going to determine what is going to happen in the future. And secondly, the history tells you about how the real world works. That's what we just did with the first 12 quarters of the data on the policing problem. There's often a scenario in which the same situation could get worse, and it will take time to fix. This one, by the way, is a real case. This is the World Health Organization's solution to eradicating polio. The Economist said that the best policy is to operate a response policy, which basically says don't do anything until there is another outbreak, and then go and vaccinate people who are in the outbreak area. That's the most cost-effective way of doing it, said the economists. No, it isn't, said the system dynamics model. And the World Health Organization changed their policy on the basis of that model. And they've embarked on a concerted campaign to eradicate polio completely in the same way as they eradicated smallpox. So what's this agile stuff? Well, here's a typical process for getting to a system dynamics model. So what you do, the first thing you do is define the scope of the problem. And that will involve lots of conversations with lots of people to make sure you're covering everything that you want to cover. You'll then have workshops and meetings with lots of people to put together a qualitative feedback diagram about how everybody thinks the situation works. And that produces something known as a shared mental model. We've got everybody who thinks they know anything about it. We've extracted their mental model of it, and we've got a big picture on the wall, and it usually is a big picture, and it usually is a big wall, of all the things that could be influencing everything else. You then throw it over the wall to some guy who knows how to use the software, and they try to turn that into a working simulation model. They go and look for the stocks and flows. They then go and try to build a working model with that, going and getting some data and seeing if they can get the model to match what they know of the real world. Bearing in mind, by the way, that after step one, we didn't bother finding out anything about the real world behavior. The only thing we found out in step one was one or two behavior over time charts of the problem we wanted to fix. We haven't done anything quantitative since then. We've mapped it qualitatively. We've put together the stock and flow and feedback structure qualitatively. Only now do we go and start looking for data. Then we try and validate and test the model, and then eventually you get some insights and some useful things that you actually can go and do. These are the characteristics. It's a qualitative approach. In the first half, you consult wider, you ask lots of people. It's whole system in scope. You do the shared mental model thing. And there are variations on this, which we haven't got time to go into, but that's essentially the way in which a lot of models are built. The problems with this are it takes too long. This can take months to get through all this. It costs too much, not only in terms of the money you've got to spend on the consultant to spend all these person days having all these meetings and doing all this discussion with people, but it costs time from the people who you're trying to help. You're taking days out of their diaries to do this, and the world's a busy place these days. Senior people can't afford to take days out. You get uncertain benefits. You don't even know if you're getting any benefits until the end of the process. And here's the killer, as far as you guys are concerned. Only experts can do this. Beginners can't do this because you've got to have high-level senior management facilitation skills. And not many 25-year-olds have got that. I know I didn't have it when I was 25. Right? This is very demanding process management stuff, right? Really, really tough. The outstanding experts at this are absolutely awesome, right? But this is real hard stuff for people to do. Turns out that this is extremely analogous to a process that dominated the field of software development for kind of right up to the 70s, known as the waterfall method. You define the scope of what you want the software to do. You go and ask everybody what they think. You ask them to write down a list of all their requests and how they think they want the thing to work. You then throw it over to an army of coders who go and try and make the software, produce the software and make it work. And 3 years later, you come back with software that costs too much, took too long, doesn't do what the user wanted. Right? Now, the IT field realized that this was not an effective way of solving people's problems 30 years ago. Now, we can build an equivalent to that for building system dynamics models. And to do that, what you need to do is you need to go back to the underlying principles of our field. The first fundamental principle is that it is about improving performance over time. If people don't get that in their heads before you start, you're definitely off on the wrong track. The second point of principle about how the method works, and again, this is at any moment in time, if you freeze time, performance at this moment is explained by the stocks. At this moment, the rate at which these offences are being committed on the London Transport Network is caused by the number of criminals who engage in these offences. That is a direct causal relationship. This stock causes that performance outcome. Right? There's another stock, which is the number of police officers. The police officers are visible on the network. So if you have more police officers, they deter the criminals from carrying out the crime. So the crime rate would be less if you've got more visible police officers than if you didn't. So two stocks, the number of criminals, the number of police officers, explain the performance outcome. And that is true at every point in time. Those resource stocks accumulate, driven by the flow rates, and decisions and external factors and existing stocks drive those flow rates. So if I were to deploy more police officers at a hotspot for these offences, I would raise the rate at which I detected and removed criminals from the system. Now, I can't just do that because police officer time doesn't come free. There's always a trade-off. So where and when do I deploy the police officers? But the decision is, where do I deploy police officers? The consequence of it is a change to the flow rate. External factors also drive these flow rates and existing stocks. So here's an agile process. Identify the outcome and produce that behavior over time chart. That's the thing we're trying to fix. Trace the causality back to the stocks. That's what we did in the first 5 minutes. We said, here's the stock of criminals, here's the crime rate that they commit. And you are already getting a working model. You're already giving somebody something that works in 10 minutes. 10 minutes you've got something that demonstrably replicates what's happening in the real world. What's happened to those flow rates? When you've added that, you've given them a further development of the working model, and then trace the causality back from each flow to the decisions and so on, and more working models and actionable findings. Now, you might need to go round this loop a couple of times, because when you've got to the flow rate, that becomes the new dependent variable. I want to explain the rate at which new people start committing this crime. That becomes the new dependent variable, and you just go straight around the same process, and you've got the second order effects. You might have to go back 3, but very rarely do you have to go around that loop more than 3 times. Okay? And you've got a pretty complete solution to the problem you're trying to do. And this is very analogous to the agile process for developing software. Extremely, I've talked with people in the information systems field, and they recognise this completely. This is exactly how they go about trying to build software. So here's the real model that we ended up building time charts of offences. The dashed lines here are the sketch data that we put in, and the solid line is what the simulation model is doing. The middle chart there is reported, detected and identified offences. And this is an important chart here. This is, where are the offenders? Where are the people who commit these crimes? Some of them are currently residing as a magistrate trader, or otherwise under surveillance. Some of them are out there and unknown. We don't know who they are, but they're out there in offences. Some of them are people we know about and keep an eye on because they've done it before. Right? So, if Johnny's not in the pub, when he's usually in the pub, he might be on committing these offences. And the sum of those is, where are all the people? Those are three separate stocks in our model. They're all criminals, but they're different stocks of criminals. Here's the first three charts. This one is the bit that we kind of did a bit of this. This is the relationship between actual offences and reported offences, and this red time series on the right is positive actions taken by the police. So they either prosecuted somebody or cautioned them, or they otherwise took some measure against somebody. Now, I said you can't solve these problems with spreadsheets, and that's because of the difficulties of handling the feedback effects, right? But it turns out you could, in principle, build a system dynamics model in a spreadsheet. You'd be mad to try, but in theory you could do it, right? And this is, what this is showing is that we're not doing anything magical here. This is simple arithmetic between these variables. Here, the reported offences is the actual offences multiplied by fraction reported. If you wanted to write that in a spreadsheet, you'd have to write something like AC $23 multiplied by $Z, something or other, right? Not exactly intuitive. In all the system dynamic software, you put in its offences multiplied by fraction reported. You don't put in codes for things, you actually put in their real names. So think of each object as a row in the spreadsheet, and think of the same formula going down all the cells in the column. That's basically, I'll go the other way around. This is the stock thing. This is the thing that says the only explanation for the number of offenders is how many were there previously, plus any new, minus any that were given up. Right? It's just axiomatically true. There isn't any possibility that anything else is happening. And that relationship continues through time, as do the previous ones. And this is the piece of the structure that captures those three populations. So the one at the top right, that's the number of people of interest, the people we're keeping an eye on. The one at the bottom right is people who are currently in the process of having action taken against them. And the ones on the left are the people who are out there at large, we don't know about them. And we just keep on spinning out these causal relationships. These are all flows that either fill up or drain the stock. And things we do mostly try to affect the flow rates. So what do we do about all this? Well, the resources we have to deal with this, at the top left we've got regular police officers. There's about 600 of them on the network. And they're doing all kinds of different things, and this is one of the things that they are sometimes asked to devote their attention to. The stock to the upper middle there is actually an example of an intangible stock. It's a skill measure. It's how skilled are the police officers at detecting these crimes. So the particular scenario I've shown here, that shows the impact of putting effort into upgrading the skills of these officers to detect these crimes. Now that's a choice. It's a costly choice. It means training. It means taking people off the task for a short time to be trained. But when you put them back on the street, they're more effective. So the number of officers multiplied by their effectiveness at detecting the crimes drives the detection rate of the crime. So we've got crimes that are being committed, but now we're actually detecting a larger fraction of them. We can improve that if we get more of them reported. So if someone is a victim of that crime and then they go and find the police officer and the police officer goes and does something about it, you've actually achieved a detection. On the right, you've got the same for covert officers. This is plainclothes officers wandering around the network, catching people before they do stuff. Right? And the same is true there, except that they are much more skilled than the average officer at detecting these particular crimes. The thing in the middle is kind of key. This is confidence in policing. This is how much confidence have the public got that the police will actually do something if they report this crime. And that number goes up if the police solve more of the crimes. So the deployment at the top raises the detection rate. The detection rate raises the confidence. The confidence raises the reporting rate. The reporting rate raises the detection rate, which raises the confidence. We've got a lovely reinforcing system going on here. Right? The more we detect, the more we raise the confidence, the more we detect. That's where you get feedback from, that kind of thing. Now, in generic terms, why do systems cause problems? They cause problems because critical factors accumulate over time. If you don't understand the accumulation process and its implications, you won't understand why your performance is doing what it's doing. The second factor is this interdependence. The crime rate itself is dependent on the number of criminals. It's also dependent on the deterrence effect of police being visible, and it's dependent on the deterrence effect of the public generally having antipathy towards this kind of offence. That's what killed drunkenness on the underground. The public just wouldn't stand for it. The public wouldn't tolerate it. They basically make it pretty clear that people who were drunk and disorderly on the tube were not welcome. There are many feedback mechanisms which can either accelerate good changes you want or accelerate bad changes. They can cause improvements to stall or to backfire. And this is an awful one. And we've got thresholds where you can put a lot of effort, a lot of money into making something happen and nothing happens, so you stop. Right? You just didn't quite get there. Things were about to change, and then you stopped. You were about to hit the threshold where this thing would go over a tipping point. So in this case, when public confidence and public antipathy towards these offences reaches a tipping point, that's when the system will start fixing itself, in addition to your policing efforts. And then we've got intangibles all over the place as well, state of mind things. As I say, system dynamics deals explicitly and quantitatively with all of these mechanisms. That's what it was designed to do. As it happens, I don't think people in agent-based modelling and discrete event simulation have quite claimed this as they can and should. They do it too, right? They deal with these things in slightly different kinds of problem spaces, right? It's just a question of getting the right tool for the job. Sometimes you need a system dynamics model, sometimes you need an ABM. I think there was a workshop, you've either had it or you're going to have it here on AnyLogic. It's coming up. AnyLogic is a software that allows you to do all three in combination. What we're finding with this approach is you get early and frequent actionable insights when you follow this approach. Another big advantage is that the people you're talking to recognize everything in the model. You don't put anything in the model that they don't recognize. Use their words. Ask them to define their words. Ask them to put numbers on what they've just described. And you'll find they can do it. What this means is that disagreements between person A and person B, each of whom has got an opinion about what's going on, that kind of disagreement tends to just melt away because you've identified what the structure of the causal relationship has been, and you've kind of fitted it out with real-world data. It's hard to argue that your opinion is right when the data clearly says something else. And you don't need to involve everybody and their art, right? You need to involve the people who know about each place, each step in its time. But do take care, because later on you're going to have to go back and win buy-in from all the other people. That, of course, is easier if the experts in the situation were themselves part of this process. So you spend less working time, you spend less elapsed time, and at much lower cost. I built a business plan for a marine engineering business with a guy over the internet in two-hour Skype calls. That's how fast I've been doing this a while, so I'm not saying that to show off. I'm saying it to show how fast you can get to a substantial solution to a large-scale issue, and other people can do it too. The next thing is it's reliable. If two people follow the same process, they should get to the same model generating the same insights. If they are two different models and they're generating the same results, they can't both be right. An elderly guy in the field who took me aside 20 years ago when I was starting, he said, "Young man," because I was quite young at the time. He said, "Young man, when you're building system dynamics models, remember this. A good model should do what the real world does, and for the same reasons. We can produce endless models that replicate what the real world does. Only one of them will do it for the same reason as the real world is actually behaving." Not always easy to get there, but that's it. This process is easily learned. It's not difficult to do. There's loads of free stuff on my site you can go for. And what that means is that young professionals can start making a difference straight away. Right? So you go and see senior managers and you start solving their problems for real in a matter of days and hours. Right? That is it's very good for you because it builds your confidence, and it's very good for your credibility, and it's very good for actually fixing the problem. You can find more at, there's a paper at sdl.re/AgileSD. That's a paper that describes this process. If you want to find out more about how to use the software, that's at sdl.re/Sysdea demos, SYSDEA. That's a YouTube playlist. It just takes you through how to use the software. And what else was I going to say? Oh yeah, if you want to play with the policing model, just sdl.re/policing1. So that there on the end is the link to the policing model that I just showed you slides of. That's the real model you can go over.
Sorry, Kim jumped in before I even got a chance to sort of welcome